Hello friends, welcome to my YouTube channel CHEMIGEEK, where we are going to dynamize our knowledge through problem solving. Today we have a wonderful problem before us which goes like this. Calculate the solubility of silver chloride in 0.2 molar aqueous ammonia if the formation constant of silver amine complex, that is AgNH₃ whole twice plus is equal to 1.7 into 10 raised to the power 7, and the solubility product, that is Ksp, of silver chloride is equal to 1.7 into 10 to the power minus 10. So before we proceed to solve this question, we need to consider understanding a few basic points that are important to solve this problem. The first one is, what is solubility? The second is, what is meant by solubility product? And the third is, what is meant by formation constant?
In the world of chemistry, solubility is a substance's ability to dissolve in a particular solvent. It's like sugar melting in your morning coffee. But what happens when you have an insoluble substance like silver chloride or AgCl? Enter solubility product and formation constants. Picture AgCl in a solution. It breaks down into silver ions or Ag+, and chloride ions or Cl. The solubility product, denoted as Kesp, is the product of the concentrations of these ions. Now add a dash of aqueous ammonia. This reacts with the silver ions to form a complex, reducing the concentration of Ag+ and in turn decreasing the solubility of AgCl. This complex plus has its own equilibrium, and its formation constant, or Kf, tells us how much of it forms in the solution. The higher the Kf, the more stable the complex, indicating a greater tendency for Ag+ to form this complex, further reducing the solubility of AgCl. So by adding ammonia, we've not only created a complex but also manipulated the solubility of an insoluble substance. Fascinating, isn't it? This is the magic of chemistry at work.
So what we can write is, according to the above question, the following chemical reaction sequentially take place. Silver chloride becomes silver ion and the chloride ion. Now when silver ion combines with two ammonia molecule, it gives the silver amine complex. Now the significant high value of the formation constant of silver amine complex indicates that the concentration of silver ion itself is quite less than the silver amine complex's concentration, which means that most of the silver ions get ammoniated, means it forms the complex. Now for silver chloride, in general, the solubility product is given by the concentration of silver ion multiplied by the concentration of the chloride ion. Now let us assume that the molar solubility of silver chloride be capital S. Therefore, the solubility product is given by the concentration of silver ion multiplied by the concentration of the chloride ion. Since both are equal to the solubility of silver chloride, this means this is S multiplied by S, which is equal to S square. Now, in aqueous ammonia solution, the concentration of chloride ion remains unaffected. That is, the concentration of chloride ion is equal to capital S. Whereas if we compare this with the concentration of the silver ions concentration, this decreases significantly, producing silver amine complex. Hence, the silver amine complex's concentration should be almost equivalent or equal to capital S. But the solubility product is equal to silver ions concentration multiplied by the concentration of the chlorine ion or the chloride ion, which is equal to the concentration of silver ion multiplied by capital S. Now, if we take this capital S on the other side of the equation, we get solubility product divided by the solubility of the chloride is equal to silver ions concentration. Now, since one silver ion requires 2 ammonia molecule to make one silver amine complex, this implies that the concentration of ammonia after complex formation which is equal to the original concentration of ammonia minus concentration of ammonia used in the silver amine complex formation. So now let us see what was the original concentration of ammonia. .2 molar aqueous ammonia is mentioned in the question. So we are putting here as the original concentration of ammonia is equal to 0.2 molar minus 2 multiplied by solubility. Now, why it is 2 multiplied by solubility? Because concentration of ammonia used for each silver by each silver ion is 2 ammonia. For each silver ion, we require 2 ammonia for the production of this silver amine complex. So we are not writing M here for 0.2 because these are only value and we are going to use this as an equation. So now this implies formation constant of the silver amine complex is equal to the concentration of the silver amine complex divided by the reactants that are 1 silver ion concentration and the concentration of 2 ammonia molecule. So when 2 ammonia molecule mixes with 1 silver ion, it gives the silver amine complex. So that is the formation constant. Is equal to the solubility S, because the concentration of the silver amine complex is also same as S, capital S, divided by the solubility product divided by S, because the concentration of the silver ion itself is Ksp divided by S, and that of the final concentration of the ammonia molecules which are remaining in the solution after complexation is 0.2. This is 0.2 minus 2S. So this is coming for the ammonia. Now for silver ion, it is Ksp by S. This is we are getting from here. And for the silver ion, we are getting it from here. So this should be the equation for the formation constant. Now using equation 1, 2 and 3, we get that the formation constant multiplied by the solubility product is equal to S square divided by 0.2 minus 2S whole square. So from where we are getting this? We are getting this from this formation constants equation. If we take the Ksp on the left hand side from the right hand side, denominator to the numerator of the left hand side, we we get a square because there was another capital S in the denominator of the denominator. So that becomes the numerator. So it is S into S is S square, and in the denominator 0.2 minus 2S whole square remains. Now, if we take this formation constant multiplied by the solubility product is equal to capital K, we get is 0.2 minus 2S whole square multiplied by K is equal to S square. So we are trying to get an equation out of it which we can solve. This implies 0.2 square minus 2 into 2S into 0.2 plus 2S whole square entire by multiplied by the formation constant is equal to S square. So we have just used the A minus B whole square formula to get this, and we have multiplied that by K, and we are getting this is equal to S square. This gives us 0.04, which is the square of 0.2 minus 2 multiplied by 0.2 is 0.8 S plus 4 S square whole multiplied by K is equal to S square. Now this implies 0.04 K minus 0.8 K multiplied by S plus 4K multiplied by S square minus S square is equal to 0. Looks like a little complicated equation, but we will be simplifying it. So if we take the common, we get from S square 4K minus 1 S square plus from S minus 0.8K into S plus 0.04K is equal to 0. Now we can see that this is turning out to be a quadratic equation where we can calculate S. Using the quadratic formula, we get S is equal to minus of minus 0.8K plus minus root over 0.64 whole square minus 4 multiplied by 4K minus 1 0.04K. So how this comes? This comes as minus B plus minus root over B square. So what is B? B here is 0.8. So if we square 0.8, or B is actually minus 0.8K, so it is K square into 0.64. So 0.64 A square is B square minus 4AC. Now 4AC, C is 0.04 multiplied by A is 4K minus 1. So if we put that here, it becomes 4 into 4K minus 1 into 0.04K divided by 2 multiplied by 4K minus 1. So in the denominator we have 2A, 0.8K plus minus root over 0.64K square minus 0.64K minus 0.16. divided by 8K minus 2. So now we can write this 0.64 as 0.8 whole square K square. Now this 0.64 can again be written as 2 multiplied by 0.8, 0.4 K plus 0.4 whole square. 0.16 can be written as 0.4 whole square. So why we are writing like this? Because we want to get, we are actually factorizing it and then we are going to simplify it. So divided by 8K minus 2. This is equal to 0.8K plus minus root over 0.8K minus 0.4 whole square. See, this is in A square minus B square formula that we have written everything in the previous step as A square minus 2AB plus B square, right? So yes, A is also present. A is here 0.8 and B is here 0.4. So if we use that formula, this can be simplified as 0.8K minus 0.4 whole square. Now this is, since this is whole square and again square root, we can write in the next step divided by 8K minus 2 is equal to 0.8K plus minus 0.8K minus 0.4. So we are removing the root, divided by 8K minus 2. Now this can have two possibilities. First possibility is when we are adding 0.8K with 0.8K minus 0.4, and another possibility will be when we will be subtracting. So first let us write when we are adding 0.8K plus 0.8K minus 0.4 divided by 8K minus 2, and another one is 0.8K minus 0.8K minus 0.4 divided by 8K minus 2. Let us write this in two different columns. S is equal to, so yes, so the left hand side possibility is equal to 0.2 multiplied by 8K minus 2. Now how this happens? We are actually taking here 0.2 as common. Why we are taking 0.2 as common from 0.8 and 0.4? The reason is that we can get 8K minus 2. You can see here. Right? So the 8K minus 2 and 8K minus 2 can be cancelled. So this is nothing but 0.2 molar. On the right hand side, if we see that 0.8K and 0.8K cancels and we get minus 0.4 divided by 8. Now we can write it as KSP into KF, which was actually the meaning of K, capital K, minus 2. Now this is equal to minus 2 divided by 2 into 0.2 divided by 1 minus 4 KSP. What we have actually done here, we have multiplied top and bottom with minus 2 so that we can easily get the answer. So it is 0.2 divided by 1 minus 4 into KSP is 1.7 multiplied by 10 to the power minus 10, and formation constant is 1.7 multiplied by 10 to the power 7. So this is equal to 0.2 divided by 1 minus 4 into 2.89 into 10 to the power minus 3. This is turning out to be around equal to 0.2 divided by 0.997. If we calculate this, if we simplify this and calculate it, we get this value. This is equal to 0.201 molar, which is also close to 0.2 molar. So the question was calculate the solubility, which is nothing but the capital S. We have got the capital S in the end, the value of capital S. So what should be our final answer? The solubility of silver chloride in 0.2 molar ammonia aqueous solution or aqueous ammonia solution is almost equal to 0.2 molar, because in both the cases we have got the same answer. And what is the significance of this problem? That you can see the solubility is turning out to be around 0.2 molar, that the solubility of AgCl becomes nearly the same as that of the concentration. The solubility of silver chloride becomes nearly the same as that of the concentration of the complexing ligand, which is nothing but the ammonia molecule. Since we have taken around 0.2 molar of ammonia, we have got the solubility of the silver ion as that, because it completely becomes soluble. So it almost reaches that concentration, which is that of the complexing agent. So I hope we have enjoyed this video. Please like, share and subscribe our channel. We can share more such problems in future.